Before we go into the main topic, force method, we are first going to discuss some of the very basics. So first of all, supports are restraints. Now you are familiar with the concepts of supports or restraints. Just a quick revision. If this is a beam simply supported at its two ends, what do we mean when we say simply supported? This is a hinge support and this is a roller support. Now why do you call this as a roller support? Why do you call it a support in the first place? You call it a support, or similarly, why do you call this as a support? You call it a support because it is capable of preventing certain displacements. For example, if you talk about this hinge support at A, it is capable of preventing a vertical translation at this location, and similarly a horizontal translation of this end. So you call it a hinge support, generally a support. So if you want to see what kind of displacements are being prevented by certain support, just draw the structural element, in this case a beam, and also draw that support at that location. Now if you see, if I apply some load to this beam, this support will make sure that this beam does not translate vertically, upward or downward. If it doesn't move upward or downward, it will make sure that this beam does not translate in the right or left direction. So it means that this support must be capable of so when we say it is preventing a vertical any vertical translation of this end, it means it is capable of producing a vertical reaction at this end if required. If the loading demands if this load is, for example, downward, this will be upward, and vice versa. So if the loading demands, this will be able to produce a reaction. So what is the difference between a restraint and a reaction? A restraint, whenever it exists, it keeps on existing all the time, no matter there's a loading or not, no matter you apply any loading or not. A restraint is something that relates to the ability of a support to prevent certain displacements. For example, in this case, this restraint, it keeps on existing whether this load exists or not. Whether there will be a reaction or not, whether this ability to prevent translation, which will be in the form of a reaction, whether it develops or not, it depends upon whether there is a loading or not. If there is a loading, if there is an action force, there will be a certain reaction developed. All right. Similarly, if we apply any horizontal load, which is not common in case of beams, but if we apply any horizontal load, this support is capable of preventing a horizontal displacement, and again its magnitude, its direction will depend upon the type of horizontal, the amount and direction of the horizontal loading that we apply, if we do. So similarly, so what will happen if only this support is present? This beam will stay at this end, will remain at its position vertically as well as horizontally, but the whole beam will translate like this. What does it mean? This beam was unable to prevent this rotation. This support was unable to prevent this rotation. So that's why when we are showing the reactions, possible reactions of this support, we only show a vertical reaction and a horizontal reaction. We don't show any moment reaction being developed. Why? Because this support is unable to prevent this rotation. So if it is unable to prevent this rotation, it actually means it is unable to develop a reaction moment that would be necessary to prevent that rotation. Similarly, if I separately draw, if I redraw this beam, if I redraw it, so now if you see the effect of this support, when you apply any loading to this beam in the presence of only this support, what is going to happen? This support is going to ensure that this end, this end B, does not move up or down. In case we apply any horizontal loading, the beam will slide horizontally. This support won't be able to prevent that horizontal sliding. So the reason you can draw the reason you show a vertical reaction at this location in case there's a vertical loading is because this support is capable of preventing the vertical movement, vertical translation of this end. So if we draw again the deflected shape in case of a loading, the same loading, it will be like this straight line, all right, with this rotation. So again, it is not capable of preventing this rotation. So whenever you show the possible reactions of this roller support, you only draw a vertical reaction. The next important concept is free body diagram. Free body diagram. So if we reconsider the beam that we just considered in the previous discussion, so again the same beam with these supports and this loading. Now, in order to study the equilibrium of this beam, I must be drawing free body diagram. Now, what does that free body diagram means? Whenever you have to draw a free body diagram, you redraw that body for which you are drawing the free body diagram. So in this case, a beam, we're drawing free body diagram for the beam. So let me redraw the beam. So here is the beam redrawn. Then start showing the forces acting on this beam. This word "on" is important. So this P force, and what other forces will be acting, what possible forces, other forces can act, these support reactions, possible support reactions. So this is what we discussed just in the previous discussion. These reactions, 2 from this hinge and 1 from this roller. So you would draw, these are acting on this beam by the supports, all right? So these reactions are, sorry. So this is complete free body diagram of the whole beam, the entire beam. So this is free, and these forces, all these forces acting on the beam are external forces to the beam. We will be discussing the topic of external and internal forces. I mean, just a quick revision. That too is just a revision, but we will be discussing external and internal forces. But whenever we draw a free body diagram for any object, we draw forces, external forces acting on that body. So this was the this was an external force, this was the applied external force, and these 3 in red are the resulting reaction external forces, all right? Extraction forces, these are the external forces. So whenever you are asked to apply equilibrium conditions, equilibrium equations, you must first draw the free body diagram. You draw the body, you draw all the forces, and if there are any moment reaction, if there are any moment forces, you must also show them as it is, all right? Show them as it is. So acting on the body, and then the objective of drawing free body diagram is to make sure that you don't miss any of the forces or moments in your equilibrium equation. Next is external and internal forces. So again, consider the same example: a simply supported beam subjected to a load P somewhere at point C. Now, if I want you to, if I ask you to show me the external forces acting on this entire beam, what are you going to do? You're going to draw a free body diagram for the entire beam. So you will draw a free body diagram like this. You will draw the element, draw the beam, whole beam, and show the forces acting on it. This P force, and then these 3 reactions due to these supports. So these are the external forces acting on this beam. All these forces are the forces acting externally on this beam, Now, if I ask you to find internal force at some particular location in this beam, internal forces at some particular location in this beam, for example, maybe at point C, at point D, let's say, somewhere over here. Now, whenever we are asked to find internal forces at certain location, we always consider what we do is, in order to be able to conceive the forces that are present at that internal location, what we consider is that if that we consider a cut through that point or through that section, and we draw one of the segments, the resulting segment. We may draw this left segment or this right segment. In this case, let me draw the left segment, this segment. So I'm going to redraw. So I have redrawn this left segment that I have highlighted in red. This point is D, and this point is, C. This point is C. So we have P force acting over here, and then we have these reaction forces AY and AX, possible reaction forces, and then we have internal forces at this location D. See, we have some names for these forces. The one which is acting normal to the section is called as normal force or axial force. Better to call it a normal force. Let's represent it by N. And then we have another force acting tangential to the section or parallel to this section is called as shear force V. And we have another internal moment which is M. So this is it. These three internal forces, these three, the ones in green, are the internal forces present in this beam at location D. So let's put the subscript D with all these forces because they exist at a particular location D. All right, now keep in mind that when you draw this left segment of the body, left segment of the beam, this left segment, all the forces acting shown over here are external with respect to this left segment. But when you consider the whole beam and you consider a cut section over here, then these green forces ND, VD and MD are internal forces acting in the beam. All right, so whenever you draw a free body diagram for a certain body, whether it is a segment of a body or it is the entire body, you always show forces acting on that body. All right, so you may ask, somebody may be confused, why didn't I show the forces ND, VD and MD in this beam? Why don't, if they do exist inside the beam over here internally, why don't I show them in this diagram? The reason is that here I am drawing free body diagram for the entire beam, and whenever we draw a free body diagram for any object or a part of it, we always show forces, external forces acting on that body. So these forces at D, which are internally present over here, are not to be shown in this free body diagram, because on any free body diagram we show only forces acting externally on that object. Why do we show them over here? We show them over here because here this is free body diagram of this only left segment. So this left segment is in equilibrium under the action of these forces, and they are all external forces with respect to this left segment. For this left segment, they are all external. You see, if these were not acting, if these I mean, if we don't believe, if somebody claims, I mean, I can't see these forces, these internal forces present, how come you show these forces? Look, if this segment, this segment in the actual beam, I mean, the actual beam doesn't consist of any segments. We are considering one part. One is to the left of D and the other is to the right of D. So if you don't believe that these forces exist, then look, this left segment is not moving up or down. It means the sum of all forces acting on this is in the vertical direction must be equal. So you see, this force is not necessarily equal to this P4 direction of this A direction AY, and P is not necessarily equal. So there must be an additional force acting over here that must be able to maintain equilibrium of this segment. Similarly, this beam is not translating in horizontal direction. So if we have a potential reaction force acting over here, there must be a potential reaction also developed on this side. Another important thing to mention is, I mean, you know that where are these two forces coming from, AX and AY? These are reactions developed by the restraint at A, by the hinge at A, hinge support at A. These forces are being applied by the right segment on this left segment. These forces are being applied by this right segment on this left segment to keep this left segment in equilibrium. All right. So, you know, if we were to draw the right segment, this segment, then, you know, the free body diagram would have been like this. In that case, you will again redraw this right segment and then start drawing forces acting on this segment. So first is this reaction By, potential reaction from restraint B, and then these are the same forces that I've shown over here, with the difference that they are shown in the opposite direction. What does it mean? This ND was acting in the rightward direction. On this segment, this was the force applied by the right segment or the left segment to keep the left segment in equilibrium, and by Newton's third law, this left segment will be applying the force in this left direction on the right segment to keep this right segment in equilibrium. Similarly, this VD is acting downward over here. It must be acting upward in this direction, same magnitude but just opposite direction. Similarly, MD and MT, these two are in the opposite direction by Newton's third law. So again, over here you can see that you must have some non-zero value for this reaction. If this P value is non-zero, so this By must be non-zero. Now this segment cannot be in equilibrium under the action of this force alone. So there must be some forces developed at the interface of the right and left segment at point D that must keep this right segment in equilibrium. So these internal forces VD, ND and MD are responsible to maintain equilibrium of this segment. So again, these are the force. All these forces shown over here are the external forces on this segment, but if you talk about this whole beam, for the whole beam, these three forces are internal forces present at point D, because we actually have considered an imaginary cut at D and exposed these forces through that imaginary cut. So to cut it short, external forces are due to support reactions, and internal forces are exposed after cutting an imaginary section in a beam. So at that location where you cut the section, you expose those internal forces. You start conceiving those internal forces. You start feeling those internal forces. All right. So now, one very important thing about external and internal forces. So now, you know, in our discussion now, we will be calling these ND, VD, and MD as internal forces in the beam at point D. And the normal force, shear force, and bending moment at point D. Very important thing to keep in mind is that As far as external forces are concerned, if you look at this beam, all these forces are all these forces shown over here are the forces externally acting on this beam. For external forces, you can draw initially when you are just starting the free body diagram. At the time of drawing free body diagram, you can show this force acting either upward or downward, doesn't matter. You can show this rightward or leftward. Similarly, this same goes over here. The initially shown direction does not matter, because once you set up the equilibrium equation, the final sign that you will get for these, for example, for AY, if you get a positive answer, what does that positive answer mean? That positive answer means that the initially shown direction on free body diagram is correct. Alright, similarly for this AX and BY, so the initial choice is not compulsory. There is no guideline regarding that. But as far as internal forces are concerned, when you are drawing this force, the ND force, normal force, this shear force at D and bending moment at D, for these internal forces, we have certain sign convention. We show them in a certain particular direction no matter what the actual force is, and then we for example, if I start solving this beam, if I start solving this segment and apply, for example, equilibrium condition submission F, no, let's apply maybe summation Fy equal to 0. So when I'm applying this, whenever I apply an equilibrium condition, I must set up a local sign convention for that equilibrium condition. Local sign convention means that this sign convention is just for this equilibrium condition. All right. So I have decided that I will treat upward forces positive. All right, and of course downward forces will be treated negative. So this is my local sign convention for this equilibrium condition. So if AY is acting upward, it will be with a positive sign. P is acting downward, so it will be with a negative sign, because it is opposite to my local sign convention for writing this equilibrium condition. So what is left now? VD. Now VD is acting downward, so it must be with a negative sign equal to 0. Now I can write down this equation for VD, solve it for VD. If I end up a positive answer, it means shear at this point is positive. It means this assumed direction of shear is correct. And if it is negative, it only means that I assumed a wrong direction for this. It actually acted in upward direction, but I have shown a wrong direction. But for the internal forces, it is compulsory that you show them acting in the positive direction. Now, why I'm showing this downward? This is important. So we have sign conventions for internal forces. So sign convention for internal forces, it is based on how an internal force deforms the body. What I mean by that? Normal force, it is considered positive when it causes elongation in the body. All right. Next is shear force. We consider a shear force positive when it produces clockwise rotation about the center of the segment. For bending moment, we consider a bending moment positive when it causes sagging. Or a better way to remember is when it causes the segment to smile. This is how, this is the smiling face. All right. So when it causes the segment to smile, you consider it positive. This is smiling. Next is sign convention for external forces. As I discussed, for external forces, there isn't any specific sign convention. You adopt a local sign convention every time you are applying an equilibrium condition. So for external forces, in fact the sign convention is based on coordinate system. All right. So you will see that based on coordinate system means that You may be calling a positive force upward, maybe somebody would like to call a downward force upward, but it's up to you. Maybe a rightward force would be considered upwards, most preferably. Maybe a clockwise or counterclockwise, whichever you like, may be considered positive. So whatever you like, it's up to you, doesn't matter. So the final result is same. So it's for the sign convention, we adopt a local sign convention for every equilibrium condition, and that's based on coordinate directions, system directions, upward. So you may say upward positive, leftward positive. Similarly, clockwise, counterclockwise positives. This is how, maybe this word positive or whichever you like. Again, I want to repeat that for internal forces, you see, I didn't say normal force is considered positive when it is acting to the right or to the left. No, I didn't say that. I said when it is causing elongation. All right. So when you draw it away from the object, it means it is trying to pull it. So you consider it positive. Similarly, for the shear force, look, shear force is a force. So it is not based on whether it is upward or downward. It is based on how it is deforming the body. If it is deforming the body such that it is producing clockwise rotation about the center of the segment, we consider it positive. Similarly, for the bending moment, it is an internal force, so I didn't mention anything like clockwise or counterclockwise. Please be very careful when you're dealing with internal forces and external forces. So internal forces, the sign convention depends on how that internal force is deforming the body. In case of external forces, we have, for every equilibrium condition, for every equilibrium equation, we choose a separate local temporary sign convention for that equilibrium equation, and then this is just something to keep account of these forces. How many forces are acting upward? What is their magnitude? So just to keep to cope with a local problem. All right. So it is based on coordinate system. Next is degree of static indeterminacy. So let's consider a simply supported beam subjected to a 6 Newton load at this location. Now, if you are interested in finding the support reactions developed, what are you going to do? You are going to draw a free body diagram for the entire beam. So this is the free body diagram of the entire beam. This 6 Newton is a known external applied force, and these 3 reactions in red are the unknown reactions. Now we have 3 equilibrium conditions available. For example, you can see, let's give them some names, A, B. So let's call this as AY, this as AX, and this as BY. Now, if we were interested in finding these reactions, we can easily do that by using equilibrium conditions. So equilibrium conditions like this: submission Fx equal to 0. So if I start solving, for example, this problem, very simple though, but let me elaborate the concept of degree of static indeterminacy from this. So looking at this free body diagram, you know that we have only one force acting in the horizontal direction, in the x direction. Although I didn't mention, but let me mention here that I'm treating x and y in these directions. All right, x, y. These are my x, y directions. So and based on these directions, I'm showing this as by, and this is ay, and this is ax. All right. So I have some coordinate system for this. Rightward positive. This is an external force, ax. So how do I deal with the sign convention? Whenever I'm writing an equilibrium condition, I choose a local sign convention for that equilibrium condition. So right now we have positive ax and no other term equal to 0. So it means ax is equal to 0. All right. Similarly, if you apply summation Fy equal to 0, taking upward forces positive, again the local sign convention is based on a coordinate system. So along positive y, I'm treating those forces as positive if they are along positive y-axis upward, and I'm taking positive y-axis upward in the upward direction. So how I solve this one now? Ay with a positive sign, y, because this is along the assumed sign convention. All right. So next, minus 6 y minus, because it is in the upward, it is in opposite direction to the considered sign convention, plus by equal to 0. All right, now we have another moment in the equilibrium condition, which is moment. Summation of moments should be equal to 0. Let's take summation of moments about a equal to 0. Again, I can choose any direction as positive. Let me choose this one as positive. So I'll be writing by multiplied by, let's show these distances. Let's say if these distances are, maybe this is 2 meters, this is 4 meters. So let me show here by into into 6 into 6. What next? By into 6 with a positive sign. Why? Because this by is producing moment about a in the same direction as the assumed positive direction for this equilibrium condition. So what next? 6 Newton force. It is going to produce moment in a sense which is opposite to the assumed positive sense. So we would be writing it with a negative sign. So this is with a negative sign, not because it is downward. It is because it is producing a moment in a sense which is opposite to the assumed positive sense. So 6 into 2, 12. All right, 6 into 2. Sorry, equal to 0, and that's it. Why? Because ax and ay are passing through a, which is the moment center, so they have 0 lever arm, so they won't be appearing in the equation. And from here you can solve by would be equal to 2 Newton. We have ended up a positive answer. Now what does this positive answer mean? This means that the assumed direction shown on free body diagram for by is correct. Similarly, you can use this equation of use this value of by over here and find the value of ay. So let me proceed. So ay turns out to be plus 4 Newton. I've just inserted the value of by equal to 2 Newton over here in the previous equation. So I've just got this value ay equal to 4 Newton. Again, this is with a positive sign. This positive sign does not necessarily mean that it is upward. It only means that it is along the assumed direction shown on the free body diagram is correct. That's it. Whatever was shown, that is correct. So in this case, I had shown it upward, acting upward. So this means that it is actually acting upward. Similarly, so we have been able to determine all these reactions acting on this beam only by using equilibrium condition. So such a structural member whose forces can be determined by using equilibrium conditions alone, such structure is called determinate structures. So degree of static indeterminacy is equal to number of unknown forces or moments together minus number of available equilibrium equations. So in this case, in this particular beam, we had 3 unknown forces, unknown reactions in this case, and those are so 3, and we had 3 available number of equilibrium equations available. So this was equal to 0. Now let's consider another example. You will see we have a vertical reaction, a possible vertical reaction, a possible horizontal reaction, and a moment reaction. Similarly, a vertical direction over here, possible vertical direction over here. All right. And so if we count the number of unknowns, unknown forces, in this case we have 4 unknowns and the available equilibrium equations are still 3. So you can say the degree of indeterminacy, structural degree of static indeterminacy is equal to 1. Alright, so let's consider another quick example. Let me show you a fixed ended beam, fixed supports on both sides. So if I again draw the free body diagram, it will consist of, you know, these forces, 3 possible directions over here. Similarly, 3 possible directions on this side. All right. So total unknowns are 6 and available equations are still 3. So the degree of indeterminacy will become, so the possible degree of static indeterminacy for fixed ended beam would be 3. But just I want to add one more thing over here. Often a beam is not subjected to any horizontal loading, so when in the absence of this horizontal loading, you will not count horizontal forces and you will not count the horizontal equilibrium equation, horizontal forces equilibrium equation. So you would say 2 equilibrium equations and you know, these, in this case, 2 equilibrium, 2 unknown forces. So you may say 2 minus 2 equal to 0. Similarly, for this beam, you may say that we have, if you are counting this force as unknown, then you must be counting summation fx equal to 0 as available equilibrium equation. So if you want to, eliminate the horizontal forces situation, so you may say 3 unknowns, 1, 2 and 3, one moment, and 2 vertical directions. So 3 unknowns, I'm not counting this one this time. So 3 minus 2 would be equal to 1 in that case, and in this case it would be like 4 minus 2 equal to 2. So we would be having, you know, 4 minus 2 equal to 2. All right. In a typical beam, what happens is that, for example, if I have let's say a prop cantilever beam, and maybe this end is A, this end is B. So as we have seen that this is the degree of degree of static indeterminacy is 1 for this beam. Even if I consider a cut section over here and I show the forces acting on the left segment, you see, and then I have some internal forces over here. Internal forces have to be drawn according to certain sign convention. So this is according to sign convention. All right, internal forces, and then this is the right segment. This is horizontal direction due to B, and then I have to draw just opposite to these forces. All right, this is the bending moment direction. So if I count the total number of unknowns, in this case I have, you know, 1, 2, 3, 4, 5, 6. These 3 have same magnitudes as these 3, so don't need to count them as unknowns. The direction is also known once you know the direction of these. So these are opposite to these, so let's count this one as 7th one. In this case, we can apply 3 equilibrium equations to this left segment and 3 equilibrium equations to the right segment. So in total, if we count, including the external forces as well as internal forces, total number of unknowns, we have 7 unknowns and the equilibrium equations are 6. So again we end up with degree of static indeterminacy equal to 1, which we had seen over here as well. The point I wanted to mention over here is that in case the same prop cantilever beam has an internal hinge, maybe over here, all right, internal hinge. Now this internal hinge is just a connection between these right and left segments. It's not a support. What happens when you have an internal hinge between two segments, then generally for a continuous beam, continuous in the sense that there's no internal hinge between any two segments. For a general beam, all segments are connected rigidly to each other, so they resist all these three types of forces: normal, shear, and bending moment. When you connect two segments of a beam with the help of an internal hinge, then that internal hinge is still capable of resisting normal forces. If you try to pull this segment, the force will be transferred to this to the other segment, so horizontal forces can be transferred across this internal hinge. Similarly, if you try to lift this segment, the other segment will also be having tendency to lift. So vertical forces can be transferred, shear forces can be transferred across an internal hinge, but the only thing that this internal hinge cannot transfer across is bending moment. What does that mean? When I'll be cutting a section over here, just as I considered previously over here, but this time we have an internal hinge over here. So when I cut a section right over the internal hinge, and I want to show the internal forces acting, these forces are still the same, just as in the previous case. These are the reactions due to this fixed support, and over here I must be showing one shear, because the hinge is still capable of producing a shear resistance. It is still capable of producing a normal force as a reaction, but it is unable to produce any bending moment. So I'll not be showing any bending moment over here, alright, because I know by the property of this internal hinge that it cannot resist an internal moment. This is the reaction due to roller support at the left end, alright, and these are the internal forces opposite to this, and similarly then we have opposite to the vertical one, shear one. So if we start counting now, we have 1, 2, 3, 4, 5, and 6. So we can apply, we have 6 number of unknowns, total unknowns, and we have 3 equilibrium conditions for each of these two segments. So in total we have 6 equilibrium conditions available. So this becomes 6 minus 6 equal to 0. Now this beam is statically determinate. Its degree of static indeterminacy is now 0. This is because of introducing an internal hinge in this beam. So the general equation for degree of static indeterminacy would be internal hinges. Alright, so let me show this like this. R for unknown forces, sometimes R for reactions, alright, minus number of available equations are 3, and then for number of internal hinges. You may remember this equation in this format. So degree of static indeterminacy is equal to R minus 3 minus number of internal hinges, where R is the total number of unknown forces. Alright. So one final takeaway from this discussion is, For determining the degree of static indeterminacy, we need to draw free body diagram for the body.